All right. So last time we talked about variables. So we talked about global variables. So basically, it's accessible from anywhere. No good for modular code because it makes it hard to actually share your functions, right? If you have global variables, because it may conflict, and you have to tell the other guy using it, hey, you have to have this variable outside every time you want to use my function. So it also may take up unnecessary memory space because even though that use the variables don't get executed anymore, they'll still be there, taking up space, which may be important when you have these tiny little controllers, much RAM. So local variables are modular. So I highlighted that second point can be implemented with registers over the stack. Yeah, you can do it with registers, knowing that others won't clog with, right? So if you have a contract between so a function is free to use all the temporary registers. Then it acts as a local variable, because after the function exits, you don't care about them anymore. But that's not something you can always assume. In the PLP CPU architecture, you have 30 registers, so that is possible. But some are 8, right? So you never assume that the register is free to use. So one way to do it, the other way to do it is to use the stack, which is how modern compilers actually do it for you. So if you have a function and you have int A, int B inside the function, enough, it will use a stack. Otherwise, it'll try to keep it in register. Any question? Variables? All right. So what do we talk about today in the next 10 minutes? So we'll talk about clock and timers. When I say clock, what's the first thing that pops into your mind?
Oscillate.
Oscillate? What else?
Counts.
Counts. Time. Right? So there's a relation between our system with time. Because so far, when you look at the CPU and the way it executes programs, there's not really a notion of time, right? You just have, okay, this instruction comes in, it jumps here, there, but you don't know like how long things take. Dictates in a CPU, well, how long do things take when it runs? The clock. You guys know what it is?
Liquid cooling CPU.
With the liquid nitrogen, yeah. Some people. All right. So what is the clock signal?
It's an oscillator. Crystal.
It could be a crystal oscillator, right? But the clock signal itself is just a square wave with fixed frequency, and that's it, right? So just a square wave. Usually, it could be generated from a crystal oscillator that you saw here at 6 megahertz. And the crystal oscillator, when you push current through it, it'll resonate and give you a very precise signal. And you can have a clock generator that actually transform this signal into a square wave that the CPU can use for everything else. How's that? Any question?
What is that on the left?
That's the crystal oscillator. So 16 megahertz.
It looks like a hot dog, or like half a hot dog.
Cheeseburgers, hot dogs. All right. Oh my God. So if you look at the clock signal, the thing that you have the clock period, so how long it takes for it to cycle, right? That's a period. And then you have a falling edge, and you have the time axis. So there are other characteristics of the clock signal, right? It's not a perfect square wave. Nothing is, right? We have finite time scale, but you can model it as an ideal square wave most of the time. The question is, see, Neo has upgraded. What does this have anything to do with the computer? Have you heard the term gigahertz, megahertz, in relation to computers? What do you think they mean?
Speed of the process.
Speed of the processor, not really. It may imply the speed of the processor, but it's not the only thing that governs the speed of the processor. Right? So there's this thing called the frequency wars, where they try to market the CPUs based on its frequency, which is not really a good benchmark of whether a CPU is better than the other.
Remember the turbo button
Oh yeah.
Yeah.
on the towers?
Why would you turn that off? No, I don't want to go that fast today.
No, your phone, if you're a smartphone, it clocks down, like if you don't use it. Like if you don't actively use it, it clocks down like less than half the clock. Yeah? Yeah. I don't need this.
You want to turn?
You have black power usage.
I don't want to play this game that fast.
So how does the clock get used by the CPU, right? So the clock synchronizes the internal CPU logic. In its heart, the CPU is still a digital logic system, right? So if you take DLD or you're taking DLD, you learn about sequential logic systems where you need the clock to actually, for the memory elements to take a new value. So if you take computer architecture, it's basically DLD in steroids, right? So if you take whatever you learn in DLD and make a CPU, which is like a huge state machine. So the clock rate determines how long certain operations within the CPU will take to a physical limit, right? Depending on your logical system, you cannot. You're not hungry. You're not yourself hungry. So the oh my God. So certain operations will need certain time to finish. So you cannot have 50 gigahertz clock and expect the CPU to go that fast. So there are things that need time to finish. But in some of the operations, it is synchronized by the clock rate. Right? In the PLP CPU, each instruction takes one clock cycle to complete. This is not true. Even your PIC microcontroller, if you use it for Admiral, different instructions may take different time to complete. Right? So you do get some sense of time, but you have to be careful. You cannot just assume that, hey, each instruction will take the same amount of time. Right? And then if you go to hertz clock rate, there are other things on the computer that cannot keep up with that speed. If you look at memory, like DDR memory, they go at 1066 megahertz. The CPU can go 4 gigahertz. Right? So how do you deal with the disparity? That's why computers, right? They try to come up with solutions on how to bridge this gap between the CPU and the rest of the systems. Otherwise, if you have a 10 gigahertz CPU and nothing else runs at 10 gigahertz, what will happen? You're just doing nothing. My laptop is currently barely doing anything. The CPU is mostly idle. Manager, CPU occupancy, 5%. Right? Just wasting energy. Well, it heats the room. Totally wasting energy. That's my justification of running all the machines in my lab. Okay, so now this is not true for all architectures, but for a PLP CPU, yes. Every cycle, you have the. Any questions so far? No? So basically, to recap, so you have the signal from the oscillator. It goes into a clock generator. It could be CPU chip, or it could be outside. And then you have a square wave coming out of the clock generator. And you may want to divide the clock to different parts of the CPU, right? Because the CPU may run at 60 megahertz, but other peripherals may run slower or faster. In some CPUs, the UART may run at the clock period, like 60 megahertz, run at half that speed. So that's why you have the clock divider, just to make sure you are in the correct timing. Because things like UART, how do you know how fast you need to send out your bit? The clock signal, right? So you have to use the clock signal to actually time all your bits. So now with the clock, now we have a notion of time in our program, right? So since the clock frequency is very close to fixed, we can relate CPU operations. For example, if we know how many clock cycles the instructions take, we can know how long the instructions will take to execute. Does that make sense? So, for example, let's say you have a CPU running at 2 megahertz, and each instruction is complete. So how many instructions can this CPU have seconds?
Is that, I mean, I know the frequency speed is kind of bogus, is flops or floating?
No, we assume that each cycle is instructions in this context, in this problem. It's not true for many things, right? For many CPUs. But in this specific example, let's say that is true. So that means, so this is 2 million cycles per second, right? So if each cycle you can finish one instruction, so in 5 seconds you finish 5 times 2, 10 million instructions. So with a 2 megahertz CPU, like an appeal CPU, you can do 10 million arithmetic operations or logical in a second, or in 5 seconds. You can't beat that as humans, right? So we did make a CPU. So beat that, computers.
Did you say full cycle is like one up and one down?
Like a sinusoid.
One rising edge and one falling edge? The cycle?
And then the next rising. So from one rising edge to the next rising edge, it's a period. It's just one cycle.
Okay.
So not just from the rising edge to the falling edge, just half cycle. That's a full cycle.
Okay.
Yeah.
Yeah. You started at the top and back up.
Yes. So knowing that, you can track time with executing instructions. So you loop, and you can calculate how many instructions you have in the loop and how many times you loop to actually delay, right? This is actually a common technique. But if your CPU is not doing nothing else, you can just delay and time it that way. It's really crude, but it works. Right? So let's say you're interior design, and then the blink the LED. And just like, you know what? I know how fast the CPU is. You just loop there and just toggle LED. But that works. It takes millions of cycles to do that, right? It's wasteful. So there are other ways to do this. The other way to do this, to keep track of time, is to use timers or counters. What do you think they are? Think about in terms of the computer. How do you think these computer architects design a timer in a CPU?
They buy a 555 timer chip.
Well, the CPU will have a regular clock signal already, right? You can clock a CPU with 555 timer. It'll be really slow, but you can. So what do you have inside the CPU? Registers. So register is some storage space you can use. So do you think a timer can be a register?
Sure.
And what would be the special thing about that register, do you think? What can you do with a register to actually give you a sense of time?
Be the counter, right?
It counts what?
Program counter?
Not the program counter, accounts payable.
Clock cycle.
The clock cycles, right? If you can have these increments or decrement on the clock cycle, that means you can actually know how much time has passed using that register. Does that make sense? All modern CPUs have timers, right? Because you need to do a lot of timing in many problems, right? You agree? Will you need a timer in your project this class? Probably not. But in many other problems, you will need to actually time things, right? So the timer is basically a register. Usually, right a reason, which we'll talk about next week, that increments or decrements every clock cycle. Some CPUs allow the timer clock to be scaled. So for example, if the CPU runs at 8 megahertz, you may want to have the clock for the counter to run at 2 megahertz. Why? More range to measure longer time before it overflows.
Because you have to count 4 cycles before it's at 1 before, so
Yes.
how is that an advantage?
Let's say you have an 8-bit timer, right? There's not many values you can hold. And then let's say you want to measure certain time that has passed. Let's say you want to measure beyond that. So you can actually get that part. But you lose precision. You can't measure smaller time values. So next week, we'll combine the timers with interrupts. So interrupts are the last thing we'll talk about, well, specific to microcomputers in this class. So after interrupts, we'll start talking about what's out there, what's contemporary things that are out there. So lab 5 will be about interrupts. So next week, unfortunately, I won't be here, but I'll be online with the Google Hangout. We'll talk about interrupts. The following week, I will have a homework about variables, timers, and interrupts. And that is, after that, the lectures will be open discussion. So I'll have some ideas what we can talk about, but it's up to you what you guys want to talk about. So it's contemporary stuff, IOs, if you want to learn about more protocols. What's CAN bus? Where do CAN bus get used?
Cannabis?
CAN bus. Cannabis.
What you said. I was like, I didn't know that.
So yeah. But interrupts is not a easy concept to grasp. That's why it's the last in this class. Right. Yes.
So is CAS latency is the same thing as a timer on a CPU, but for RAM? Are those related?
No. We can talk about memory if you want. There's so many things in computer engineering, so they're all pretty cool. So I'll have things that we can talk about. Otherwise, I'll just ramble on. Right, so you can direct me after the next 2 weeks. All right, we'll have which teams presenting? ABC and sensors.
Yeah.
Yeah, all right.
Yeah.
All right, I'll see you tomorrow.